So welcome to Math 150, Section 2, 2021, Lecture 8. And so what we're going to do today is we're going to talk a little bit about the notion of the derivative, how you define it, how you actually compute it. So has anybody ever seen this function before? F of x equals x to the 1701. Okay, so you've never seen it before, but I somehow suspect that you can differentiate it. So what is f prime of x? What would f prime of x be?
1701
x to the... All right, so we're not going back to the definition of the derivative. We're not going back to f prime of x is the limit as h goes to 0 of x plus h minus f of x over h. What we do is we've created a rule, the power rule, the derivative of power. And now that we know that, we say, oh, okay, we know the derivative of x to the n, we take n equals 1701 and we use that. A lot of math is like it. You spend a lot of time with the definitions, you prove some theorems and results, and then you never go back to the definitions when it's time to do things in practice. You always look at the consequences. It's important to know why things are true. It's important to know what conditions must be satisfied to use them. But from a practical perspective, you don't compute by going back to the limit. Now, if I give you the series, the sum, and goes from 0 to infinity of x to the n, this is 1 plus x squared, and this is 1 over 1 minus x, if the absolute value of x is less than 1. So the point of this is, if the condition is satisfied, if absolute value of x is less than 1, then we immediately know what the value of the sum is. When we come to what it means for a function to be differentiable as a function of several variables, we will talk about what needs to be satisfied. And then for the most part, we will forget that. And just, you should always check to make sure the conditions are satisfied, but for the most part, the functions we look at are going to be nice and they will exist. I will talk a little bit today about a function that is not differentiable, even though a lot of the partials exist, to just illustrate what can go wrong and why these are reasonable conditions. I'm not going to give the full rigorous proof as to why what I'm going to show later is enough to imply that the function is differentiable. So the function we're going to look at that causes a lot of problems is f of xy is xy to the 1/3. And it turns out that this is a bad function. Bad for differentiability. In other respects, it's actually not so bad. What are the two biggest fears when you're defining a function that might cause it not to exist? What are the things we have to be careful about? Dividing by 0. We're clearly not dividing by 0 here. That's good. There's one other concern that sometimes arises.
Negative under a radical?
Yes, negative under a radical. We're taking the square root of a negative number. Well, here it's actually the cube root, so we're fine. What's the cube root of 8? What's the cube root of negative 8? Negative 12, so that's actually okay. Now, we went a little bit wrong. I think I almost support it by saying, what is the cube root of 8? 2 is a cube root. How many cube roots of 8 should there be? 3. There is a formula for the roots of a cubic. It's painful. There's one for the quartic. It's even worse. And beyond that, there's no longer a general root. But this is a particularly nice one. It allows me to talk about some memories that you might have from high school that have been repressed. We know x equals 2 is a root, right? That means the polynomial x minus 2 divides this. And this is polynomial long division. Right? Does that sound vaguely familiar? So we now can do polynomial long division to see how many times x minus 2 goes into this. Or we can use the method of divine inspiration. The way the method of divine inspiration works is you go like this, you go, ah! And then you write down the answer. And so I claim this is the same as x minus 2, x squared plus 2x plus 4. That the difference of two cubes factors like this. And we can check. X times x squared is x cubed. X times 2x is plus 2x squared. Minus 2x squared, they cancel. 4x minus 4x minus x. Yes, it works. And then how would we solve x squared plus 2x plus 4? Quadratic. So we can actually write down all the roots of 8. There is one positive root, 2, but there are 2 other roots as well, and they occur in complex conjugate fields. If we had instead of x cubed plus 8, we would be fine, the root would be negative 2. So in terms of this function, it's not so bad that we have a cube root. Square root would be a little bit worse. Cube root is okay. What is f of 0y going to be for any value of 1? 0. What about f of x0 for any value of x? 0. So we have a function that is 0 along the x-axis and 0 along the y-axis. If you think of your function, f of x over here as distance, what would the derivative represent? So if f represents distance, what does its derivative represent? Your speed. And so imagine I tell you, for all units in time, my distance from the origin is 7. Am I going to make the track team for my speed? What's my speed? 0. If my distance is always constant, my speed is always 0. So if I have a function that's 0 along the x-axis, if I take a derivative along the x-axis, what do I expect to get? 0, I'm not moving. If I take a derivative along the y-axis, what do I expect to get? 0. Let's calculate. Let's look at df dx at 0, comma y. So what might you expect this to be? Well, let's do the calculation. This is going to be the limit as h goes to 0 of f of 0 plus h minus, 0 plus h comma y minus f of 0y divided by h. It's the limit as h goes to 0. What is f of 0y? 0. Okay. So I don't even have to worry about that term. 0 plus hy, this is just going to be hy to the 1/3 divided by h. Which is larger, h to the 1/3 or h? So h is bigger than h to the 1/3. Let's say h is 1 over 1,000. What's h to the 1/3? 1 over 10. Let's say h is 1 over 1,000 cubed. H to the 1/3 is 1 over 1,000. If you're less than 1, if you take the cube root, you're actually going to get larger. You'll get closer to 1. So which is going to be larger, h or h to the 1/3? H to the 1/3 is going to be larger. And so we're going to be taking h to the 1/3, we're going to be dividing by a number that's much, much less than it. It's going to blow up. This is going to just become the limit as h goes to 0. We'll have h to the negative 2/3 y to the 1/3. And what is h to the negative 2/3 going to do as h goes to 0? This is going to be the same as having an h to the 2/3 in the denominator. This is going to be the same as the limit as h goes to 0. I can pull out the y to the 1/3. It's 1 over h to the 2/3. And that's going to be infinity. It's going to blow up. That's bad. What went wrong here? We thought that maybe the derivative should be 0. But let's look at what we're computing. point 0, comma y. And so when I'm taking the partial derivative with respect to x, I'm not traveling in the vertical direction. I'm traveling horizontally to that point. Now my function is continuous. F of xy is a continuous function. But it's 0 along the axes, and as we approach, the approach is such that when we take this quotient, it blows up. The
How is it
function,
continuous?
I'm sorry?
Sorry, how is it continuous?
Well, just the function f of xy is xy to the 1/3. That's just a continuous function. If I just take the cube root of a function, it's still continuous. If you change x and y by just a little bit, f of xy is not going to change by that much. If you want, you could take some point x plus delta x, y plus delta y, and take this to the 1/3 power. I can pull out an x and a y from both of them. I'll assume x and y onto 0. I would have xy to the 1/3, 1 plus delta x over x, to the 1/3, 1 plus delta y over y, to the 1/3. So as long as x and y on 0, as delta x gets really, really, really small, this is going to come very, very, very close to 1. I'm not really moving that far from xy to the 1/3. And if either x or y is 0, then it's much easier. So the original function is continuous. The problem here is I'm approaching this point horizontally. How should I approach this point? Vertically. And so if I approach this point vertically, I will now get the derivative is 0. Because along the y-axis, what do I know about the value of the function? It's not changing. It's 0, but it doesn't, but the not changing is actually what really matters. The value doesn't matter. The fact that it's not changing means that the partial derivative would be 0. If I choose the point x comma 0 and ask for the partial derivative at this point with respect to x, I would compute df dx at the point x0. This is the limit as h goes to 0, f of x plus h0 minus f of x0 over h. Well, what is f of x0? 0. What is f of x plus h0? Because the y-coordinate is 0, both of them are 0. So this would just be the limit as h goes to 0 of 0. Because when you have h going to 0, h is never 0. You've never divided by 0. This is one of the easiest limits to calculate. For every value of h, I give you 0. What do you get as h goes to 0? What if h went to 5? What would you get? What if h didn't go to anything? Just h hopped all over? Still gets 0. It's always 0. So the partial derivative does exist with respect to x here. It doesn't exist with respect to x over here. This should tell us that something is wrong. That even though this function looks nice, it has some issues. Well, let's try to understand what those issues are. So let's say I want to take the partial derivative of xy to the 1/3. I'm going to take the partial derivative with respect to x. So I'm treating y as a fixed value. So this is going to be the same as y to the 1/3 d by dx of x to the 1/3. What's the derivative of x to the 1/3? Good. So it would be 1/3 x to the negative 2/3 y to the 1/3. Again, this is what I would get if I just played things formally, just did things as I would have done in Calc 1. As long as x and y are on 0, I can easily do this. Is this a good function, or does this function have any issues? Yeah, there's division by 0. So it's not continuous at places where x equals 0. And that's the cause for the problem, is that the partial derivative does not exist at x equals 0 when we try to do this calculation. Or that if I do the calculation, I can calculate like this for any value of x that's not 0, and then if I take x equals 0, and I go back to the definition, I would get 0 because everything is 0. The two are not the same. And so my function is going to have problems because the partial derivatives are not existing and continuous. So issue, partials are not continuous. And that's going to lead to the big theorem that we're not going to prove, but it's at least worth knowing. So theorem, if the partial derivatives exist and are continuous, then the function is differentiable. Yes?
What does it mean for partial derivative?
So it just means that the function itself is continuous.
Oh.
So over here, if x and y are not 0, this function actually exists and is continuous. But if I allow x to be 0, then all of a sudden things blow up, because as this approaches 0 from x being positive, this is going to go up to infinity. But if I go back to the definition of the derivative and I calculate df dx when x equals 0, and y equals 0, if I try to calculate it at that point, I would get 0. So if I try to calculate the partials at 0, 0, if I come in through points when x and y is not 0, it blows up. If I come in along the x-axis with y equals 0, I would have 0 every single time. So the partials are not the same. There's a problem with the partials. And it makes sense. If the partial derivatives have an issue like this, it's not unreasonable that the function is not differentiable. Okay. So if you come back over here, this is the advantage of working on the blackboard, is I can change things very quickly. Instead of talking about h going to 0, instead of using the point x, I could use the point x naught. Does that make any real difference? No. And instead of saying h going to 0, I could instead say, well, rather than h going to 0, let's have x goes to x naught. And the h would become x minus x. Does that make any difference? No. And then it'll be a little bit cleaner later if rather than using the point x naught, I use the point a. It'll just make the algebra a little bit nicer. And this way, I'm taking derivatives with respect to the variables, but I don't want that to also be the point because I could be a little bit confused as to what I'm doing here. We talked about how we could rewrite this as the limit as x goes to a of f of x minus f of a minus f prime of a x minus a over x minus a equals 0. And all we did is we just took this, brought it over to the other side because it's a constant, you can bring it inside the limit. We multiplied by x minus a over x minus a, so we have a common denominator. And the way to view this is the tangent line approximation. F of x is where am I? F of a is where I started. F prime of a is my instantaneous speed. And x minus a is how much time has elapsed. So this is saying that to approximate where you are at time x, look at the tangent line approximation. And it's so good that when you divide by x minus a, it's still going to be very accurate. The difference is going to be small. We want to generalize this. And we want to talk about a function to be differentiable. So we want to just maybe start replacing x's and a's with vectors. The problem is I can't divide by a vector. You know, everything up here, f of x and f of a is going to be a number. I can't divide a number by a vector. So rather than saying that this equals 0, a better way of viewing this is I'm going to divide this by the absolute value of a, and I'll put an absolute value upstairs as well. If I change to vectors, what do you think x minus a is going to change to? So I can't divide by a vector. I can't divide by the vector x minus a. So rather than dividing by the vector x minus a, what associated quantity should I divide by? It's magnitude. So I'm going to replace these with vectors. And then the question is, what is f prime of a over here? So we'll call that the derivative of f. Now, what kind of quantity is x minus a? It is small, but what kind of quantity? It's a vector. What kind of quantity is f of x? We have a function of several variables. What is the output? Is the output a number? Is it a vector? Is it a matrix? When we had f of xy is xy to the 1/3, was that a vector or was that a number? It's a number. We're dealing with functions that take xy, xy, z as input and then give you back a number. So f of x is a number. F of a is a number. This better be a number because we can only subtract like objects. So if I have f of x minus f of a, this has to be a number. X minus a is a vector. What do you think might be really nice for d of f to be? If this is a vector, I need to somehow get from a vector to a number. Do you know any way to get from a vector to a number? Dot product. So what if this was a vector of derivatives and we have a dot product? So if we were to do that, and so we'll say df at the point A, often written as an upside down triangle at A, now grab f at the point A is the vector df dx1 at A df dxn.
Wait, what does grad f mean?
These all mean the same thing.
Oh.
They're all the same. This is a generalization of f prime. Do not write f prime when you are doing a multivariable calculus. If you have a function of several variables. When you write prime, it's not clear what you're talking about. When you use a capital D, this means the vector of all the partial derivatives. When we plug that in, this is basically the same as saying we're looking at the limit as x goes to a of f of x minus f of a minus df dx1 of a x1 minus a1 plus, put this all in brackets, df dxn of a xn minus an divided by the length of x minus a. This is the tangent hyperplane. It's the dot product of the vector of derivatives with how much you've moved. This is your normal direction. This is the equation of the tangent. This is the equation of the hyperplane, or the equation of the plane that we talked about. If I give you a normal, it's going to be all things perpendicular to that. We're taking the dot product like this. Yes?
For that equation over there, is the numerator an absolute value? Or...
If you want it to be. It doesn't matter. Because what kind of object is the numerator? Is the numerator a number? Is it a vector? Is it a matrix?
No.
It's a number. So if the whole thing is going to 0, I don't need the absolute value upstairs. I can put it in. It's not wrong to put it in. I only need it downstairs because x minus a is a vector, and I can't divide by a vector. But the numerator, I can do either way. So what we're saying is for a function to be differentiable, we need to be able to subtract off the tangent hyperplane, and it needs to be so good that even when we do that, it's small. So if I give you lots of nice functions, if I give you f as a polynomial in the variables x, y, and z, then you can go through and you can show that these limits will exist. If I give you a trig function involving sines and cosines, it exists. If I give you exponentials, it exists. If I give you product of polynomials and trig functions of exponentials, it exists. What if I give you ratios of polynomials? Are you a little bit worried if I give you a ratio of polynomials? So what could happen if I give you ratios of polynomials? What you have to worry about with ratios of polynomials? Dividing by 0. So if I give you your f is maybe x squared plus y squared divided by x, y, z, well, maybe it's not going to be differentiable. So for the most part, if I give you nice things, this is not going to be any problem. And you'll be able to calculate the derivatives. We do not want to have to go back, though, to the definition of the derivative. We don't want to calculate the tangent plane and show that no matter how you approach, you always get the same answer. We want to just compute the derivatives. And so we want to use the rules from Calc 1. So mathematicians are lazy, and it's a good thing to be lazy. You always want to reduce what you're given to something you already know. We know how to do one variable calculus. So I want to reduce the new stuff here to one variable calculus so we can use those results. Most of you, not all of you, had never seen the function x to the 1701, but it was no problem to differentiate that. You didn't have to go back to the definition. What we want to do is we want to build up rules for differentiation so that if I give you more complicated functions now, you can take the derivatives. So let's say I give you f of x, y, z is x squared y z cubed. And I want to calculate the derivative with respect to x. So d by dx of x squared y z cubed. What have I done wrong? I can't just write d by dx floating by itself. D by dx is an operator. What does it act on? The function f. I can write what the function is and say it's acting on the function, just write it out, but I can't just write d by dx equals. D by dx does not equal that. D by dx applied to f is equal to this. All right? How would I take the derivative of this? Well, yz cubed is just a constant. So this is just going to be yz cubed times d by dx of x squared. What is the partial derivative of x squared with respect to x? 2x. This is the same as a normal derivative. So this is going to just be 2xy z cubed. So we can use the results from calculus. Just y and z are along for the ride. So I could start trying to build up more interesting things. I'm only going to work with functions of two variables. If I can do things for 2 variables, do you think I can do it for 3 variables? Yeah, the notation just becomes a little bit longer. And so rather than having longer notation, let's have shorter, more compact notation. Let's just do things with 2 variables. Do you think the first thing I should look at should be the product of 2 functions and try to calculate what's the derivative of the product? Is that the first thing I should look at? Or is there something that I should look at maybe first that's a little bit easier than the product? Yeah, I should probably start off with the sum. And I can ask, well, if I have A is the sum of f and g, what would the derivative of A be? So dA dx would just be d by dx of f of xy plus g of xy. And if you go back to the definition of the derivative, which fortunately has not been erased yet, you just see, oh, well, look, if I've got f and g and they're just being added, I can group all the f's together here and all the g's together there, and it's just going to be the sum of the derivatives. And so when the dust settles, it's just going to be df dx plus dg dx. And that's what you would get for the first component. You would have the same thing for the second component. So you would have, dA is df plus dg, or grad f plus grad g. Sometimes, in a little bit of an abusive notation, we don't write the point at which we're evaluating this. And frequently what you might do is you will have x, y, and z be your variables, and you will evaluate the derivative at x, y, and z. Usually it doesn't cause too much of a confusion. In Calc 1, I give you the integral from 0 to 1 of f of x dx. What is going from 0 to 1? X. Do I need to write x equals 0 down here? No. Is it a good idea to do so? In multivariable calculus, yes, when you have several variables in play, then it's very useful to have that. But if you only have one variable, there's really no need to do it. All right, so this is the sum rule. The derivative of the sum is the sum of the derivatives. Note that the derivative is going to be a vector. It's df dx1 all the way up to df dxn. Or if you want df dx, df dy, df dz, if we only have 3 components. And so here, this is one vector equals the sum of 2 other vectors. If I had a difference, no big deal. If I had a constant multiple, if I had 5 times f, then the derivative would just be 5 times. And this is essentially saying if at every moment of time you are 5 times the distance from home as before, you must be traveling 5 times faster. Another way of looking at it is how do you convert from yards to feet? Yes, I started in yards and I want to go from yards to feet. 1 yard is how many feet? 3. So if I measure things in feet rather than yards, my speed is going to look 3 times faster. Is my speed physically 3 times faster? No, but in this unit, it's going to look 3 times faster. The curve would look identical. All that would change is the scaling on the axis. Now, the more interesting case is going to be, what if I have a product instead of a sum? So what I want to do now is A of xy is f of xy, g of xy. And I'm going to first try to calculate the derivative with respect to x. And the goal is to try to understand the derivative with respect to x. So this is d by dx of f of xy, g of xy. But I can write this in a way that I think will be a little bit more illuminating. It's the partial with respect to x. And I'm going to write script f subscript y of x, script g subscript y of x. So basically just tell me, I'm considering y fixed, So I'm going to call that new function for fixed value of y, script f sub x, or so script f sub y of x. Does this look like a Calc 1 problem now? How would you take the derivative of this? Partial. So it'd be the derivative of f with respect to x times g plus f times the derivative of g with respect to x. So it's convenient if you want to introduce new letters to remind ourselves, we've seen this before. But we can also just do it the long way. It's going to just be df dx times g plus f dg dx. Is everybody comfortable with how we get this? So this is going to be the first component of our derivative. So we have, this is going to be dA dx. If instead of having the partial with respect to x, I had the partial with respect to y, is it going to be a hard calculation? You're just going to be search and replace. So when the dust settles, I have dA equals grad A equals grad A equals dA dx dA dy. And now I can just fill in what it is. The first one, dA dx, is going to be df dx g plus f dg dx. And now I have the derivative with respect to y. All that changes is I replace the x's with y's. And so I will get partial f partial y times g plus f times partial g partial y. All right, this is looking promising. It should be a vector with two components. I've got a vector with two components. Now, the goal is to try to do some algebra to rewrite this in a more illuminating manner. So I have four objects. Two in the x component, two in the y component, two in the first component, two in the second component. I can write this as a sum of two vectors. What do you think I should pair with df dg? Should I pair it with df dy g or f dg dy? 50-50 chance. Df, which one? Df dy g. Why should I pair this with this?
Both have the G.
They both have a g, and these both have. Yeah. So if I do that, I can view this as df dx g, comma df dy g plus f dg dx f dg dy. Now what can I do here? So both of these have a g in them. What can I do? Take it out. Is g a constant? Is g a vector? Is g a matrix? What is g? This is just g of x, y. This is just a number. So this is going to just be df dx df dy times g. And the second one is going to just be f times dg dx dg dy. Okay. What is df dx df dy? How can we write that more compactly? What is that equal to? The gradient of f, or df, capital D. So this is just dA is dF times G plus F times dG. Or if you want, the gradient of A is the gradient of F times G plus F times the gradient of G. Does that look like the product rule from before? No. Do we ever have a vector times a vector? No. We're very careful. Gradient of F or dF, these are vectors, and we're multiplying it by the scale of g of xy. Similarly, dg is a vector. We're multiplying it by the scale of f. Perfectly fine. What this is telling us is that if we have a function that can be represented as a product of two other functions, the derivative of the product is still essentially this combination of the functions and the derivatives. We just have to be careful now because derivative in multivariable calculus means the vector of partials. And so we have a beautiful formula like this. If I give you two functions and I ask you to find the derivative, one thing you could do is you could just multiply everything together and take the derivative. But if you happen to already know the derivatives of each piece, it makes no sense to combine them and then differentiate. If you know the derivatives, this allows you to interpret the derivative of the product in terms of the derivatives of the constituent pieces. So whenever possible, it's nice to understand a complicated object by trying to break it down and understand simple ones. Do you think that there is a quotient rule? Right? What part of the quotient rule do you not like? Or if you like every part of the quotient rule, what part do you think I don't like?
Oh, the denominator?
I'm sorry?
The denominator?
Yeah, the denominator. It would be so much nicer if we didn't have that g squared down below. As we go through all of this, well, instead of having f of x times g of f, if I just did f divided by g, I would put a division here. How? It would just go through like standard quotient rule. And I would have a g squared over here with the x's, and I would have a g squared with the y's. It would just propagate nicely. So the quotient rule is going to be extremely similar to what we have. It's not going to be a big deal at all. Anybody ever read click, clack, move, how's that type? So it starts, Farmer Brown has a problem all day long. His cows like to type click, clack, move, click, clack, move, click, clack, move. And so I use this when I teach calculus. When we get to the Farmer Brown problem, you might remember this with help, that Farmer Brown loves rectangular pens, and he will not consider any pen other than a rectangular pen for his cows. And given the mascot of this fine institution, we should be very concerned with how we fence in cows. Does anybody remember if you have a fixed amount of fencing, what is the best way to divide it if you have to do it in rectangles? Of all the rectangles with a fixed perimeter, which one has the largest area? Square. And it turns out after a while, you come across this function that you need to differentiate. How would you take the derivative of this function? What rule could we use? Yes, that's the better way to do it. What rule could you use? You could use the product rule. You could say it's the derivative of x times 1 minus x plus x times the derivative of 1 minus x. However, rather than using the product rule, if we just expand x minus x squared, I would much rather expand and then do the difference rule than not expand and use the product rule. So whenever you're doing any problem, you always want to stop and think before you do algebra, is this the algebra you want to do? So I am thinking of a New England transcendentalist writer who I believe is the patron saint of mathematics, for the wonderful advice he has written. Anybody know which New England transcendentalist I am thinking of? Thoreau, excellent. And I think our textbook does it say like the early transcendentalists or something like that on the title of the last book? Yeah. I don't think they mean the transcendentalist writers. So what is the line from Thoreau that I'm thinking of? Simplify, simplify. Now, if you wanted to, how would you simplify, simplify, simplify? Simplify, simplify would be simplified to simplify. I think he does two simplifies to just really drive home the point. Before you start doing a tremendous amount of algebra, what should you do? Stop and think, is this the best way to go? When I was taking a complex analysis exam as an undergraduate, there was a problem and I filled up 2 pages with long calculations, and I knew that I would get the right answer if I just continued, but my God, it was going to take a long time. And this is a 50-minute in-class exam. And I wrote, there's got to be a better way of doing this, and I stopped and I thought about it, and then I just solved the problem in a few lines, because this is an in-class exam. Is the professor going to give us something that requires 40 minutes of filling up pages? Does the professor want to grade something that is going to take all of it? No. There's got to be a deeper, better way of looking at it. It's sadly in storage, so I can't show it to you, but the professor wrote in the margins, it's about time you realize that, Steve. And he was right to put that on my exam, because I should have realized from the beginning in an in-class exam, there's no way that this is the problem he wants me to do. There's got to be a better way of looking at this. We've seen this, I think, when we did telescoping sums. 3 minus 1 plus 17 minus 3 plus 181 minus 17 plus 24601 minus 181. What is this equal? 24,600. Because things just cancel like this. Before you do a calculation, think, what's the best way to do it? What do you know? How can you use what you know? For this, yes, we could use the product rule. I don't want to use the product rule. When we have a product of functions, it's not unreasonable to think maybe it would be a good idea to use the product rule to take the derivative of the product. Right? And then we have a little bit of time that we didn't have in section 1, so I'll end with the following problem. Let's say f of x is x times natural log of 5. As an aside, once you get to college, we often write this as x times the log of 5. We stop using ln for natural log in college because we always work with the natural log because the natural log is basic. And the derivative of the natural log is much nicer than the derivative of the other ones. You don't have any problem. What rule could I use to take the derivative of x times the natural log of 5?
It's a constant.
It's a constant. So this is just the natural log of 5 times the derivative of x, or it's just the natural log of 5. What's another way you could take the derivative of x natural log of 5? What's another rule you could use? It'll take a little bit longer, but it will work. You could use the product rule. It's a little bit of an overkill to use the product rule when you have a constant as one of your terms. Right? The constant rule, if you want, is actually a special case of the product rule. It's much faster to just use the constant rule. It's not wrong to use the product rule. And if you have something that will work, step 1 is solve the problem. Then, once you know how to solve the problem, then it's solve the problem efficiently, quickly, well. But make sure you have a way that will work, that will get you to the answer. So for a lot of problems, you will have more than one way to go. It's not a bad idea to spend a few moments and try to think, is this how I want to approach it? For some problems, I'm going to ask you to do it multiple ways. And this is a good habit to get into because if you can do a problem multiple ways, this is a possibility to check your work. Should you get the same answer if you check it multiple ways? Yeah. If you don't get the same answer, what does this mean?
You did it wrong.
At least once, possibly twice. There's a lot of things where they do that tell me 3 times. Where in the military, they will have 3 computers calculate a trajectory for an attack. If 2 out of 3 match, they fire. It's not guaranteed to be correct, but if two of the calculations are right, the odds are you calculated it correctly. Anybody ever see the movie Minority Report? Tom Cruise is in it. It's based on a short story by, I believe, Philip K. Dick, who's responsible for a lot of stuff from Terminator to Man in the High Castle. And that is an interesting situation where you have three objects that must agree. And at one point, two of the three agree, but not for the reason you think. And so sometimes it is important to see the work. The other reason I want you to be able to calculate things multiple ways is sometimes this will show you how much better one way is than the other. And we'll see that as we get to the chain rule, which is the most painful of all the rules. It gets really bad in several variables.